Okay, so we're ready to start the second part of the morning session, and the first talk of this part of the session will be given by Laetitia Bettmann on trajectory-unravelling in a mesoscopic leads approach.
Thank you, and thank you to the organizers. As already announced, I will be talking about the trajectory unraveling in the mesoscopic leads approach, which is an ongoing work in collaboration with Michael Cumming, Gabriel Landi, John Gould, and Mark Mitchison. So let me give you a brief motivation of what it is we're studying and why it is connected to what we're discussing here. So we would like to characterize currents that are exchanged between open quantum systems and their surroundings. And a system that's interacting with its surroundings typically exchanges energy in various forms. So either through the flow of heat or particles as sketched here, and these currents are typically driven by gradients in either the chemical potential or the temperature. Now, we're interested in fluctuating currents because they contain information that's relevant both for understanding the system and its surroundings. And
yeah, so that should work now, I think. Right.
Yeah. Okay. Now, in order to study the impact of quantum and environmental fluctuations that occur during the evolution of the central system of interest, one typically has to go beyond studying averages over ensembles. So that's where the tool of continuous quantum measurement comes in. So assume you measure transitions of particles between baths that your central system is connected to. Then that will yield you an output current, which can be described as a stochastic incarnated time series of jumps. So you assume you have, for example, a central system of a double quantum dot. You perform a measurement on it, and you obtain this record. Then this will not just tell you the particle current, but it's also a way for you to reconstruct the state conditioned on your jump record in time. So once you reconstruct the state, you can then, for example, compute observables like the double quantum dot occupation as a function of time conditioned on your measurement record. Now, if you repeat your experiment many times, you can then answer the question of, for example, what is the probability for a total charge n to pass through your system up to a certain time t? So that's plotted here for many different runs of the same experiment. And we see that by sampling, we can reconstruct what can be usually computed using full counting statistics, namely a full distribution Pn of t that yields time-resolved information about the fluctuations. That's of particular interest, for example, in transient regimes. So in non-transient regimes or in non-equilibrium steady states, we encounter a very familiar quantity, namely the diffusion coefficient, which appears as the second scale cumulant, which is the time derivative of the variance of the integrated current. So that's just the slope here, and appears in, for example, the thermodynamic uncertainty relations we've discussed before. Now, let me kind of wrap up my motivation and formulate an aim for this talk. So I want to present to you how we trajectory unravel the dynamics of the mesoscopic leads approach, which I will now introduce, and use this as a tool to analyze fluctuations in currents. And we take inspiration for our previous example of using these measurement records to reconstruct states. So, as I said, I will briefly introduce the mesoscopic leads approach, and then show you how to trajectory unravel states using descriptions that prescribe well the conditional dynamics of the state, and show you how the emergence of an integral fluctuation theorem comes about, and leave you then with a conclusion and an outlook. Now, this toolbox that I've been mentioning before is the mesoscopic leads approach, and it's basically an approach to accurately model physical reservoirs, which are typically assumed to contain infinitely many modes. The key idea here is to approximate this reservoir by a finite number of damped modes. So we want to describe this red box here by what's here in this shaded red area. So the key idea is to introduce these damped modes. There is L of them. and all of them are connected to their individual baths. These modes we summarize as the lead, and we assume that they're weakly coupled to individual baths at the same temperature and chemical potential of the original bath we model. Now, we can make a cut through the system after the lead node, so to speak, and define an extended system which is now comprised of all the lead nodes and the system nodes, so everything that's in this orange box. And because these lead nodes are only weakly coupled to individual baths, we can use a very familiar tool, namely the master equation, to describe the evolution of the density matrix of the full extended system as a function of time. So this here is the form of the Lindblad-Master equation for the density matrix of the extended system, where H is the Hamiltonian of the extended system. And these are just the jump terms that describe hopping in either direction on all of the lead nodes. So the Hamiltonian of the extended system might have arbitrary time dependence in the system Hamiltonian. Then there's a term describing the Hamiltonian, describing the lead, and the Hamiltonian that is typically of the form of the hopping Hamiltonian that describes interactions between the system and all of the individual nodes. Now, what's kind of the benefit of going through this procedure? Well, one of the benefits that is quite striking is that you can reconstruct an arbitrary bath spectral function, J of omega. Why? Because all of those lead nodes individually see a flat spectral density from the bath that they're coupled to. But the system from each of the lead nodes sees a Lorentzian spectral function. That means if you kind of weigh them and center them at different energies, the energies of the lead nodes, you can reconstruct in this way an arbitrary spectral density in this sum. Another key advantage is that you can describe strong coupling to an environment. Oftentimes you're restricted in your description to studying systems that are assumed to interact weakly with their surroundings. Why? Because this allows for a clear separation between what's the system and what's the environment, and you can describe the system somewhat separately and assume that the reservoir is stationary. But here you, since you kind of make this cut at a different stage, namely after the leads, the system can interact strongly with the lead modes, but overall you can still describe the dynamics of the extended system by Lindblad-Master equation. Another thing that I've already briefly mentioned is that the system Hamiltonian may have arbitrary time dependence. This is important because usually for external driving, exact treatment is difficult. Even for periodic driving, one usually has to rely on perturbative expansions in either the frequency or the driving strength. But here, the time dependence must be neither periodic nor so that's kind of a key advantage. And our goal now is to extend this toolbox that I've now described by a method to study fluctuations of output currents. Well, that's one of our goals, and output currents that would be obtained in continuous measurement. Why? Because we want to go beyond the information that we can obtain in ensemble averages, or dynamics that are described at the level of ensemble averages. And this might be relevant then for studying fluctuation theorems, or, for example, relations that describe an interplay between the entropic cost or increasing precision or signal-to-noise ratios. Here, we will focus or restrict ourselves to fermionic systems that have a quadratic Hamiltonian at the level of the extended system, so Hamiltonian is of this form. The reason being that Gaussian fermionic systems, or for Gaussian fermionic systems, the covariance matrix fully encodes the state. So the covariance matrix has matrix elements Cij, which are just these correlators here with respect to the density matrix, and that's true. Or the covariance matrix fully encodes C because because rho can be written in terms of two matrices M and Z that purely depend on the covariance matrix. Now, why do I go through this, or why is this useful? Well, it's useful because the dimension of the matrix rho is 2 to the n by 2 to the n, whereas the dimension C is just n by n. Now, it's known already that at the level of the ensemble average, you can describe the time evolution of the system by the covariance matrix in this differential matrix equation, which is of the Aponov form, and W and F are matrices that depend on the single particle Hamiltonian of the extended system, the rates, the jump rates, and the Fermi functions evaluated at the lead mode energies. But I said that we want to go beyond the ensemble average and want to know about the full distribution. If we can't compute it, then one way to go about it is to sample from it. So we have to be able to compute single trajectories. Now there's two things that we need to know in order to construct trajectories, basically. We need to know how does the system evolve in between jumps. So this is called the no-jump conditional evolution. And then we need to know how to update our state given the knowledge that a jump has occurred at a certain time, or at certain times. So let me first speak about the no-jump evolution. So we find that the covariance matrix again follows a matrix differential equation where the matrices V and B again depend on the single particle Hamiltonian of the extended system, the Fermi functions evaluated at the lead mode energies, and the coupling rates to their individual baths. Further, you need to know the survival probability of a post-jump state, meaning that's the probability for your state to survive up to a certain time, or for no jump to occur up to a certain time. And we find this form, which again only depends on these matrices I've introduced before. So you will see an exponential drop of the survival probability as a function of time. And then we also found equations which describe how to update the covariance matrix given that a jump has occurred in channel K. So for example, if a jump occurs on the kth lead mode and it's a jump onto the lead mode, then you update your covariance matrix in this way. And then in this way, if the jump happens in a way where a particle leaves the lead mode. And of course, the survival probability will be reset to 1. So once you know this description, you want to implement it numerically, and you do that in a Monte Carlo fashion, where you first draw a random number between 0 and 1, this random number. Then you time evolve the covariance matrix and the survival probability according to the equations I've shown you before. And once the survival probability hits this random number, a jump occurs. So that's how you kind of compute Tj. Then you draw a second random number, again between 0 and 1, and you compute the probability for a jump to occur through a given channel. So that's given by this expression, and you evaluate that at the time that you want the jump to occur at. Now, then you sum up all of these probabilities until you hit the second random number that you've chosen, and then you update the state according to the jump equations that I've shown before. So that's kind of expressed here. Now we have all the ingredients to simulate single trajectories, and this is shown here for a simple example of a double quantum dot connected to two baths that are modeled in the fashion of the mesoscopic leads approach with 10 lead modes per bath. So here you see in orange and green the time evolution of the occupations of the double quantum dot, and then in the light red and blue you see the time evolution of the lead modes. And in the lead modes you see these jumps according to which the survival probability is reset to 1, and also the occupations in the central system change. And then I would like to also briefly show you some results on the emergence of the fluctuation theorem. So let's start from the second law of thermodynamics, which states that changes in the entropy due to irreversible processes are positive. Well, that's valid in macroscopic thermodynamics, but is a bit blurred in the quantum world because here it only verifies on average. So in continuous measurement, you have to describe the entropy production as stochastic. And this stochastic entropy production becomes then a measure of irreversibility along single trajectories. So this is expressed here, where the entropy production of a single trajectory going from time 0 to tau is given as the log of the ratio between the probability for the trajectory to happen in the forward direction and then for its time-reversed counterpart. So it's easy to show then from this expression that once you average the exponentiated negative entropy production over all trajectories, you arrive at 1. So the stochastic entropy production can be split into two parts. One that is associated with system changes along the trajectory, and an entropy flux that's transmitted between the system and the environment. And in the two-point measurement scheme, which I'll just explain in a second, this is apparent as well. So this is the term relating to the system state change, and this is the term related to entropy flux transferred between environment and system. So in the two-point measurement scheme, or the two-point measurement scheme works as follows. So you start in an initial state, and then with probability p and 0, you project into one of its eigenstates. Then you let the system evolve according to its conditional evolution, and you arrive at a final state, and that one you project into the unconditionally evolved initial state, so into one of those eigenstates. So you have a measurement at the beginning, at the front, and the probability p and 0 is related to the measurement at the beginning. And then the backwards process, in the backwards process, you start with the unconditionally evolved initial state of your forward process, project into one of its eigenstates, and that's probability p and tau. You again let the system evolve, but according to the time reverse evolution, and then you project again into an eigenstate of the initial state that you started with in the forward process. That's a bit complicated. Just remember that the probabilities come from the two-point measurement, or from the projections at the beginning and end of the two-point measurement scheme. And then there is this term related to heat currents that are exchanged between system and environment. And this term here is just a sort of heat increment associated with a single jump for a given mode. So here you sum up jumps in all lead modes, and you integrate over time, and you recover a sort of heat flow. Okay, and then our results show that the interval fluctuation theorem is satisfied, at least in the high temperature limit that we've studied so far, in a minimal setup containing a single quantum dot coupled to a bath at temperature T and chemical potential mu. And here I plot this average as a function of number of trajectories that we average over. So the bath consists either of 10 lead modes that are damped or 5 lead modes that are damped. And we see that as we increase the number of trajectories that we average over, we recover, or the integral fluctuation theorem emerges. Now I'd like to conclude. So I've shown you a numerically efficient method to simulate trajectories in open quantum systems that are connected to somewhat realistic reservoirs, depending on the number of lead modes you choose, in the so-called mesoscopic Leeds approach. This allows us to access time-resolved full distributions of integrated currents. And I've shown you that we tested its convergence by verifying the emergence of an integral fluctuation theorem. Now, this I think fits into the picture of this conference because it allows us maybe in the future to investigate trade-off relations by understanding the interplay between entropic cost and terms like precision, accuracy, signal-to-noise ratios that we've heard about throughout this conference. And with that, I conclude and I'd like to thank you for your attention.
Thank you, that was really very clear. Although one thing I wasn't quite clear on is experimental setting for what you have in mind here. So perhaps I just don't understand all the ins and outs of mesoscopic electronics, but the way that experiment would normally be done with the double dot is with a current, with the thing embedded in the circuit and a current flowing through the device, and you could either measure the current through the device or use a quantum point contact to measure the charge on the dot. But here, I think you don't have in mind a current flowing through the device. It's some sort of short-circuited device where you actually monitor the chemical potentials in the reservoirs. Is that the experimental setting you have in mind?
Yes, I mean, in a way, we...
Well, just that one. Oh, yes. There.
Yeah.
That one there.
I mean, in principle, we want to measure transitions between bath and
Yeah.
meat. So we just would assume something like a detector of clicks.
Right. But I think you have to be a little bit careful about the experimental setting there, because if there's a current flowing through the device, jumps on the dot and jumps off the dot, contributing the same way to the current, because they both just either draw in an increment of current to maintain chemical equilibrium or push out an increment of current. It always goes in the same direction. But that wouldn't be watching jumps necessarily. But I guess you could consider a short-circuited thing where you could literally monitor the chemical potential in one of the...
I mean, in a way,
strands.
we don't really monitor the transitions between the system of interest and the bath. We kind of monitor something that's internal to the bath.
Yeah, that's what I'm talking about. So if you can monitor the chemical potential in the bath, watch it fluctuating. Every time you add a dot, add an electron, it goes up a little bit, and every time you take one off, it goes down. So it's very close to your model. It first enters well above the Fermi level in the drain, say, and then rapidly thermalizes to the reservoir. It's very much like your Leeds model. But somehow you've got to be able to monitor that change in chemical potential. Unless I've misunderstood the experimental setting.
Yeah, I can maybe comment on that. I mean, I personally have in mind actually just the conventional measurements that, I mean, in terms of experiment that we'd like to use this to model, it would be the conventional experiment that you would do in mesoscopics where you have an ammeter, essentially.
Current.
But then, of course, you can't actually monitor all of the clicks that the teacher is simulating. So the simulation is just a tool to get to what we actually want, which is the distribution of essentially integrated current, which you can measure. The individual jumps wouldn't be resolved in that way, but this is just an efficient way of getting that distribution, if that makes sense.
Okay. Yeah.
I can ask this is either a very naive question or whatever, you can let me know if it is. But from what I saw, you're only able to recover this fluctuation relation at specific, like when T is very big, right? Like when you don't have that in the finite temperature regime, like you don't have a fluctuation relation. And there is this work that John did with Kevin Modi, where they look at getting integral fluctuation relations from a TPM, but for channels in general, not for like a Lindbladian setup. And there, what they show is that you get an integral fluctuation relation when the channels are unital. And like the non-unitality is what doesn't, like sort of messes the fluctuation theorem. I know it's very hard to relate channels to Lindbladians, but like, have you thought of somehow taking inspiration from this work, or what this insight from non-unitality could mean in this context?
As of now, I'm not sure.
Just thought it might be interesting.
Thank you.
Hi, I was wondering, is it possible to extend that setting to include more sites inside the system?
Oh, yes.
Yeah. And like, would that be able to be simulated in the same way, or are there different effects that you would expect?
Yeah, I mean...
If you have thermodynamically many points in between?
Yeah, I mean, this is just a placeholder, really.
Okay, but then maybe I missed that. How did you... the dynamics in the system could be anything. You were not specifying it. I see. Okay.